In this video, we will take a look at what is called the dot product. In previous videos, we used what we called scalar multiplication to lengthen or shorten or even change the direction of a vector. This was done by multiplying the vector by a constant, which we called a scalar. For example, given the vector 2, -1, a new vector, 3 times that vector, could be found by taking the constant or the scalar of 3 and multiplying it by each part of the original vector to get 3 times vector v is equal to the position vector 6, -3. The dot product is another type of multiplication, but it involves multiplying two vectors. The result is a scalar or a constant. For example, given the position vector a, b and the position vector c, d, the dot product v dot product with u is the sum of the product of the horizontal components and the product of the vertical components. Or we could say that the dot product would be equal to a times c, so those are the horizontal components, plus b times d. And let's take a look at an example so that we can see that this really does end up equaling a scalar or a constant. So in this example, we're asked to find the dot product of position vector 2, 5 and position vector u, -3, 8. So I'm going to write the dot product of those two vectors, and I am going to take the horizontal components, the 2 and the -3, and I'm going to multiply those, and I'm going to add to that the product of the vertical components, so 5 times 8. So that gets me -6 plus 40, which is equal to, positive 34. So the dot product is simply a number which we said we could call a constant or a vector, a scalar. So what does the dot product help us determine? Well, the dot product provides a direct way of determining the angle between two vectors. And I say direct because the angle between two vectors can also be found using right triangle properties, but would require some extra work. So we say that to find the angle theta between two vectors, where theta is between 0 and 180 degrees, so the angle is between 0 and 180 degrees, we can use the formula where the cosine of that angle is equal to, up in the numerator, the dot product of the two vectors, and in the denominator, the magnitude of each of those vectors being multiplied. A proof of this formula can be found using this YouTube link if you're interested. Let's look at an example. Find the angle between the vector, which equals vector v, which equals 2 times unit vector I plus 3 times unit vector j, and vector u, which is 4 times unit vector I minus unit vector j. Okay, so here is what we're going to do. And just to give us a visual, I'm providing a graph so that we can actually graph this to see if the angle between the two vectors makes sense to us. So the way that this is written for vector v, it's written as a position vector. So if I start at the origin and I move 2 unit vectors along the horizontal axis and 3 unit vectors along the vertical axis, I end up in this first quadrant. Okay, so this is going to be vector v. Okay, let me switch to red, and I'm going to go ahead and plot position vector u, which is starting at the origin also, but now moving 4 units to the right and 1 unit down. And so I get that vector in the fourth quadrant. Okay, so The red in the fourth quadrant represents position vector u, and the blue in the first quadrant represents position vector v. And I think we can pretty clearly see that there is some angle measure, right? There is an angle measure in between. Now, I mentioned before that this angle between two vectors formula is really nice because it gives us a direct way of finding the angle between these. And I said direct because we could use right triangle properties. What I'm talking about here is, I could drop some perpendiculars and I could certainly find the angle between position vector v and the horizontal axis. And then I could drop another perpendicular for position vector u, and I could find the angle between that vector and the horizontal axis, and then I could add those two angles together. That's definitely doable. Just going to take a little bit more work, I think, than this is going to be. So let me show you how this is going to work. This formula says that the cosine of an angle is going to equal the dot product. So what is the dot product of these two vectors? So let me just do this off to the side. So the dot product between v and u, we learned is the product of the horizontal pieces, so 2 times 4, and then we're going to add to that the product of the vertical components, so 3 times negative 1. And so that gets me 8 plus negative 3, which is 5. So up in my numerator, where I found the dot product, I'm going to put a 5. Down in the denominator, I need to find the magnitude of each of those vectors. So what is the magnitude of vector v? Well, that is going to be the square root of 2 squared plus 3 squared. I'm getting the 2 and the 3 from the components of that vector. And let's see, 2 squared is 4, 3 squared is 9. So I think I get square root of 13. Square root of 13. And for vector u, I'm just going to leave that as the square root of 13. I'll do approximate answers in a minute. For vector u, that's going to be the square root, the magnitude is going to be the square root of 4 squared plus negative 1 squared. And that's what, 16 plus 1 or 17? So that's going to give me the square root of 17. So I'm going to put those two numbers in my denominator. So square root of 13 times the square root of 17. And so now I'm going to say that theta is equal to cosine inverse of 5 over, now the square root of 13 times the square root of 17, I can actually do that multiplication. 13 times 17 is, I think, 221. Okay, and so I'm going to put all of that into my calculator, and when I put that in, and it doesn't tell me to round, but I'm going to go ahead and round to maybe 1 decimal point, I get approximately 70.3 degrees. So let's go back to our picture. Does it look believable that that black angle there, which I will call theta, so theta is that whole angle, is it believable that that's around a 70 degree angle? And I would say yes, it is believable. So going back to the idea of the dot product, what exactly is it that that dot product indicates? Well, we can examine this by using the formula for the angle between two vectors to sort of explore this. There's the dot product up in the numerator. Because the denominator of this formula is always going to be positive, right? Is that true? It is going to be true because the denominator is just the product of the two magnitudes. And magnitudes, these are magnitudes. Magnitudes are just lengths, aren't they? They're just lengths. And so those are always going to be positive. Okay? So therefore, let's just make a couple of observations here. Let's say if we're talking about the cosine of theta, and we know that that denominator is always going to be positive, let's just look at a couple of scenarios. What if the numerator, the dot product, what if that dot product is also positive? Okay, so this is the example where the dot product is greater than 0, right? It's positive. Well, what does that tell you? Let's think about a circle for a second. If in a circle, right, we are limiting ourselves to only angles between 0 and 180 degrees, right? So we're just talking about quadrant 1 and quadrant 2. If the dot product is positive, then that means that the cosine of theta is also positive, right? Because a positive divided by a positive is a positive. Okay, so we're talking about what angle, when you take its cosine, is positive. Well, in quadrant 1, so we're limiting ourselves to quadrant 2 and quadrant 1. In quadrant 1, the cosine is positive, isn't it? Sine is also positive. In quadrant 2, the cosine is negative and the sine is positive. So if the dot product is positive, then what that tells us is that the angle between those vectors is an acute angle. What is an acute angle? Acute angle is an angle that is between 0 and 90 degrees, right? Has to be in quadrant 1. Okay, let's take a look at another scenario, and I'll just draw a line here. What if now, right, we still have that positive magnitude down in the denominator, but now let's say that the dot product, what if it equals 0? Well, 0 divided by any number is 0, isn't it? So now we're asking the question, what angle would produce a cosine that's equal to 0? Going back to our picture on the unit circle, we know up here at 90 degrees that that ordered pair is the ordered pair 0, 1. That's a cosine of 0, isn't it? And so what we can say is that if the dot product is equal to 0, then the angle between the vectors is 90 degrees, isn't it? Has to be 90 degrees. Now, if you've got the angle between two vectors as 90 degrees, then that means that the vectors are perpendicular, right? Another word for perpendicular that you'll see used a lot in trigonometry is orthogonal. Orthogonal. O-R-T-H-O-G-O-N-A-L. Orthogonal. Okay, let's look at the one last scenario. What do you suppose that last scenario is? The last scenario is where we have a negative up in the numerator. So now the dot product is less than 0. Well, I think we sort of addressed that in our picture, didn't we? A negative divided by a positive is a negative number, And so now it's saying, okay, well, what angle produces a cosine that's negative? If we are limiting ourselves only from 0 to 180 degrees, then that has to be the quadrant 2 angle, doesn't it? Has to be the quadrant 2 angle. So in quadrant 2, the angle between the vectors is obtuse, or we would say that it is between 90 degrees and 180 degrees. 180 degrees. So what we're saying is, for example, in that last example that we looked at, I think we were asked to find the angle between, I don't have a nice place to put this, but let me just refresh your memory. We had a position vector that was 2, 3. I don't think we wrote it like that, but that's another way of writing it. The position vector u was at 4, -1, and we found that the dot product was 2 times 4, which was 8, plus 3 times -1, which gave us -3. So we found that the dot product was 5. Now, knowing that when the dot product is greater than 0, which it was in this case, we could have said with certainty that that angle between the vectors would need to be an acute angle between 0 and 90 degrees. And if you go back and look at your notes that you just took from the previous slide, you will see that ultimately we found that the theta was about 70 degrees. I think we said 70.3 degrees. So if you need to find an exact angle, then yes, you do need to go through this process of actually finding that angle between two vectors. But if you're just trying to get a general feel for how large is the angle between the two vectors, then all you need to do is just find the dot product and then use the things that we just discovered to make a determination about the size of that angle.